Today I'll be going over video homework 3. I'll explain how to do these 5 problems step by step, covering things like binomial distributions, the central limit theorem, confidence intervals, hypothesis testing, and t-procedures. Let's go ahead and get started. Our first problem tells us a basketball player makes 80% of her free throws. Suppose she takes 60 shots. Then it asks, identify the parameters of the binomial setting, n, p, 1 minus p, and explain what each represents. We'll begin by going over our parameters. So, n is the number of trials. So in this case, it would be 60, since that is how many shots she's taking. P is the probability of success, so the probability of making the shot, which would be 80% or 0.8 when put into decimal form. Then to find the probability of missing your shot, we do 1 minus p, so 1 minus 0.8, and get 0.2. Moving on to question 2, it asks us, compute the mean and standard deviation of the number of successful shots. Clearly explain what these numbers mean in context. In a binomial distribution problem, we find the mean by multiplying our n times p. So here it would be 60 times 0.8, which would give us 48 as our mean. Now, this means our player can be expected to make about 48 shots. Now for standard deviation, which tells us how much the successful shots may vary, our formula is standard deviation equals the square root of n multiplied by p multiplied by 1 minus p. Then we plug in our values to make it the square root of 60 times 0.8 times 0.2. Then when we solve, we get the standard deviation is approximately 3.1. All in all, this tells us in most cases she'll make about 48 shots, give or take about 3. Now we can go to question 3, which asks us to check whether the normal approximation of the binomial distribution can be used here. Show the values of np and n1 minus p and verify that they satisfy the rule of thumb that np is greater than or equal to 10 and n1 minus p is greater than or equal to 10. So this one is fairly simple, since all we need to do is check that n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. Here, n times p is 48, and n times 1 minus p is 12, so both are greater than 10. This tells us that the normal approximation can be used here. Moving on to question 4, it asks us, use the normal approximation to estimate the probability that she makes at least 50 shots. We will do this by using the normal distribution with our mean of 48 and standard deviation of 3.1. In a problem, we must add a continuity correction. Because this is a binomial distribution problem, we subtract 50 minus 0.5 to plug into our problem. Our problem would look like this. C equals 49.5 minus 48 over 3.1, which would be about 0.48. When we find 0.48 in the z-table, we see that it gives us 0.6844. Then to find the right tail probability, we subtract 1 minus 0.6844 and get 0.3156. This tells us that there is about a 31.6% chance that she makes it at least 50 shots. Moving on to question 5, it asks, Reflect, in your own words, why do statisticians sometimes use the normal model for binomial probabilities, even though it is only an approximation? To answer this, statisticians use the normal model because it makes calculations more simple when there is a large number of trials. Despite the calculations not being exact, the results are very close. Now that we've completed all the questions from problem 1, we can move on to problem 2. It tells us, a population has a mean of 60 and standard deviation of 12. Samples of size n equals 36 are taken. First question asks, what is the mean and standard deviation of the sampling distribution of the sample mean? So the mean of the sampling distribution is always the same as the population mean, so it would just be 60. For standard deviation, which would actually be standard error in this case, the equation is standard error equals standard deviation over the square root of n. When we fill this in, we have 12 over the square root of 36, and when we solve, we get standard error equals 2. Moving on to question 2, it asks, what is the probability that a sample mean is greater than 63? Show all steps of your calculation, including finding the z-score. To standardize this, we would have the equation z equals 63 minus our mean 60 over our standard error 2. When simplified, we have 3 over 2, which would be 1.5. When we find this in the z-table, we get 0.9332. We would then have to subtract from 1, so our answer would be 0.0668. This would mean there is about a 6.7% chance our sample mean is greater than 63. Now we can go to question 3, where it asks, on a normal curve, sketch and shade the area that represents the probability found in part B. Clearly label the mean, the sample mean of 63, and the corresponding z-score. To start off, all you do is draw a horizontal line and a bell curve. Then I labeled my mean of 60 in the center. Next, I marked the units above and below the mean according to the standard error, like 60 plus 1 standard error, 60 plus 2 standard error, and so on. Now I've added the sample mean of 63, which is 1.5 standard errors above the mean. Then I shaded to the right of that line we made since we want the probability that the sample mean is greater than 63. Using the standard normal, Pz is greater than 1.5 is approximately 0.0668, meaning there is a 6.7% chance the sample mean exceeds 63. Writing that, as well as the shaded area, shows us that small probability. Now we can move on to question 4, which asks us to explain how the central limit theorem allows you to use the normal model for the sample mean, even if the population distribution is not normal. The central limit theorem says that if the sample mean is large enough, the distribution of the sample mean will be approximately normal. This still applies even if the population itself isn't normal. Because n equals 36 is greater than 30, the rule does apply here. To move on to question 5, it asks, suppose the sample mean increases to n equals 100. How would the standard deviation of the sample mean change, and what does this mean in practical terms? If we increase the sample size to n equals 100, we would do 12 over the square root of 100, and we would get 1.2 as our new standard deviation. This would mean the sampling distribution would become narrower. Practically, this tells us larger samples produce more consistent averages. For question 6, it asks us, Explain how the law of large numbers relates to this situation. What happens to the sample mean x as n becomes larger and larger? The law of large numbers means that as we take more and more samples, the sample mean gets closer to the population mean. The larger the sample size, the more accurate our estimations will get. After doing all the questions for problem 2, we can move on to problem 3, where it tells us a random sample of 50 students has an average GPA of 3.15. Assume that the population standard deviation is 0.40. Question 1 asks us to construct a 95% confidence interval for the population mean GPA. Show all steps and formulas clearly. To construct our interval, we would first write out the formula. Confidence interval equals sample mean plus or minus z times standard deviation over the square root of n. Then we plug in our values to get 3.15 plus or minus 1.96 times 0.4 over the square root of 50. Then when we calculate that and get 3.15 plus or minus 0.11. When we subtract 0.11 from 3.15, we get 3.04. And when we add 0.11, we get 3.26. This gives us our two numbers for our interval. Now for question 2, it asks, interpret your interval in context. What does the 95% confidence level actually mean? This means that we are 95% confident that the average GPA for the entire population is between 3.04 and 3.26. This means that this method captures the true mean 95% of the time. Moving on to question 3, it asks, on a normal curve, sketch the confidence interval centered at the sample mean. Clearly label the mean, the lower and upper bounds, and shade the region that represents plausible values for the population mean. I first just drew the horizontal line in the bell curve. Then I drew my center at the sample mean, 3.15, and the lower bound, 3.04, and the upper bound, 3.26 from our confidence interval. Then I shaded the area between 3.04 and 3.26 that represents the middle 95% of possible sample means. Now we can move on to question 4, which says construct a 99% confidence interval using the same data. Compare this new interval with the 95% interval. How does its width change and why? To do this, we use z equals 2.576 and then solve it in the same way we did for the 95% confidence interval. We can do 0.4 over the square root of 50, which would be 0.0566, and then multiply by 2.576, which would give us about 0.146. Then we can round and add and subtract 0.15 to 3.15 and get an interval of 3, 3.3. This interval is wider since we are being more confident and covering more possible values. Now for question 5, it says, suppose the sample size is doubled to n equals 100, while the sample standard deviation remains 0.40. Recompute the 95% confidence interval and compare its width to your answer in part 1. Explain why the change occurs. To do this, we first find the standard error by dividing 0.4 by the square root of 100 to get 0.04. And that is shown here. Then we find the margin of error by multiplying 1.96 by 0.04 to get 0.078. Then we add and subtract 0.08 and 3.15 to get our interval of 3.07, 3.23. When our sample size gets larger, the interval becomes narrower since we have more information and less uncertainty. Next, we can go to question 6, where it asks, in your own words, summarize how changing the confidence level and changing the sample size affects the width of a confidence interval. To answer this simply, having a higher confidence level makes the interval wider, since we want to be sure that we capture the true mean. In addition, having a larger sample size makes the interval more narrow, since larger samples are more exact. Moving on to problem 4, it tells us the soda company claims that their cans contain, on average, 12 ounces of soda. The consumer group suspects the mean is less. They take a random sample of 40 cans with a sample mean of 11.92 ounces. Assume that the population standard deviation is known to be 0.24 ounces. It then asks us, state the null and alternative hypothesis clearly. Is this a one-sided or two-sided test? Explain why. To answer this, the null hypothesis is mean equals 12, which represents the company's claim, and the alternate hypothesis is mean is less than 12, which represents what we're testing for. This is a one-sided test because we're only looking for one thing, which is seeing if the mean is smaller. Now we can go on to question 2, which asks us to compute the test statistic and find the p-value for this test. Show all steps. We first set up the equation z equals sample mean minus hypothesized mean over standard deviation divided by the square root of n. When we plug in these numbers, the equation looks like z equals 11.92 minus 12 over 0.24 divided by the square root of 40. When we calculate that, we get negative 2.11. When we find negative 2.11 in the z table, we get 0.0174. So our p would be 0.0174. Moving on to question 3, it says, at the 0.05 significance level, what is your conclusion? Write your answer in a complete sentence in context. Using the 0.05 significance level, we can see that p equals 0.0174 is less than 0.05. We would reject the company's claim or the null hypothesis. Now for question 4, it asks, on a normal curve, sketch and shade the area that represents the p-value. Clearly label the population mean, the sample mean, the test statistic, and the rejection region. Indicate whether it is a one-tailed or two-tailed test. We'll start off by just making the curve, and then we'll mark our line in the middle showing our mean of 12. Then we mark our standard errors. I showed the work on how to get the standard error, in this case 0.038, below the curve. I then marked 1 standard error above the mean and 3 below. I then marked the sample mean on our curve, as well as z equals negative 2.11. I then shaded to the left of 11.92 to represent our p-value. Then I labeled the critical value, x equals 11.9375, and shaded to the left of that to show the rejection region. Then I wrote that 11.92 falls in the rejection region. Now we can move on to 5, which asks, conceptually, what does the p-value represent in this situation? Explain what a small p-value tells us about the evidence against the null hypothesis. The p-value is the probability of getting results this extreme if the claim of the companies were actually true. The small p-value means our results are very unlikely under the null hypothesis, which leads us to reject it. Now we can move on to problem 5, our final problem. It tells us a nutritionist wants to test whether a new diet changes the average cholesterol level from the historical value, 200 milligrams per deciliter. A random sample of n equals 15 people on the diet has a random sample mean of 194 milligrams per deciliter and a sample standard deviation of S equals to 20 milligrams per deciliter. Assume the population is approximately normal with no strong outliers. With that, we can go to question 1, which asks, state the null and alternative hypothesis to test whether the diet changes the mean cholesterol level from 200 milligrams per deciliter. Is this a one-sided or two-sided test? Explain briefly. The null hypothesis is mean equals 200, and the alternate hypothesis is mean does not equal 200. This is a two-sided test because the mean could be higher or lower. Moving on to question 2, it tells us compute the test statistic and the degrees of freedom. First, we would set up the equation t equals sample mean minus the hypothesized population mean over the sample standard deviation divided by the square root of n. Then we plug in our values to make it 194 minus 200 over 20 divided by the square root of 15. That would give us approximately negative 1.16 as our answer. Moving on to question 3, it asks us to find the critical value t for a two-sided test at 0.05 with your degrees of freedom. Decide whether to reject or fail to reject by comparing the absolute value of t to t. For a significance level of 0.05 and degrees of freedom of 14, our critical value is plus or minus 2.145. Since our absolute value of t is 1.16 is less than 2.145, we fail to reject the null hypothesis. There isn't enough evidence to say the diet changes cholesterol levels. For question 4, it says, on a t-curve centered at 0, sketch and label the two critical cutoffs at plus or minus t, mark your observed t-value, and shade the two rejection regions. Clearly indicate why your observed t falls in the fail to reject region. First, I just drew a regular bell curve, marking 0 as the center, and our critical values plus and minus 2.145. Then I shaded the rejection regions. Then I marked our t-value, negative 1.16, to show it is not in the rejection zone. Now moving on to question 5, it asks us to construct a 95% confidence interval for the true mean using the t critical value. Explain how the interval supports your decision in part 4. First, we set up our equation, 194 plus or minus 2.145 times 20 over the square root of 15. We would get 11.08 for that value, so we would have 194 plus or minus 11.08. When we add and subtract 11.08, we get 182.9, 205.1 as our interval. Since 200 is inside this range, it supports our conclusion. For our last question, it asks, explain how Inference using the t-distribution for a population mean is similar to and different from the z-based significance tests. To answer this, both tests compare how far a sample mean is from the hypothesized population mean. We use the t-test when the population standard deviation isn't known and when the sample is small. The t-curve is also wider because smaller samples have more uncertainty. That completes all 5 problems. After our review, I hope you have a better grasp on these concepts. Thank you for watching.